हाँ अच्छा, ये आप फोटो लगा के बैठे हैं ना, आप बैठिएगा वहां पे जहाँ पे आपके चेहरे पे रोशनी पड़े, अंधेरा अंधेरा ना लगे। हाँ, और सर बात करेंगे 1 मिनट।
हाँ बुद्धू नमस्कार। वो जो आप मेल लिखे थे ना, वो रसिया वाला नहीं दे पाएगा, ये उसका तबीयत ठीक नहीं है।
हेलो हेलो,
अभी वेट कीजिए, अभी वेट कीजिए।
अच्छा अच्छा, पहले आप शुरू करेंगे?
हाँ हाँ, वेट फॉर सम टाइम।
ओके ठीक।
आप सर मत बोलिए। शुरू कर दें?
देखना चाहते हैं उसको तो हटाए ना, बस इसको बोलिए ना हटाने के लिए सर। इसके
बोलते हैं शुरू करते हैं।
अच्छा हाँ।
Good afternoon to all of you. So now we will start our after lunch session, and I invite Dr. Bidubhushan Sahu, Associate Professor, Department of Physics, KIIT University, to chair the session. So Dr. Sahu, please take over the session.
Okay, thank you, madam. Am I audible, madam? Hello.
Sir, voice is a little bit slow.
Am I audible now? Hello. Am I audible now?
Sir, it's not that clear.
Hello.
Yes, sir,
Now
you
I am
can
audible?
start now. Yes, sir, start now.
Okay. Thank you, madam. Good afternoon, everyone, and welcome you all once again to AFM 2020. I, Dr. Bidubhushan Sahu, extend a warm welcome to Dr. Diptiranjan Sahu at AFM 2020 of our school, Department of Physics, KIIT University. I find immense pleasure in introducing our honorable speaker, Dr. Diptiranjan Sahu, who is currently an associate professor of physics in the Department of Natural and Applied Sciences at the Namibia University of Science and Technology. He received his PhD degree in physics from Institute of Material Science, Utkal University, India. After his PhD, he has worked as postdoctoral researcher and visiting scientist faculty in several institutions such as National Taiwan University, National Cheng Kung University, Taiwan, and University of South Africa. His research focus is on multifunctional materials, including nanomaterials, ceramic, composites, spintronics, magnetic materials, and application of functional materials in devices. He has, to his credit, he has published more than 90 international peer-reviewed journals, one book, 2 book chapters, and more than 100 research articles in conference proceedings and meetings. Dr. Sahu has also been awarded Australian Research Fellowship, Spanish Government Excellence Research Fellowship, and as rated researcher of NRF South Africa. He has also served as reviewer of many journals and editorial board members of few journals, and the principal investigator of some international projects. Once again, I welcome Dr. Diptiranjan Sahu. So, and again, I also, I'm very thankful to Dr. Parasar, convener of AFM 2020 and the whole organizing team for giving me this opportunity. Once again, I welcome you all, and welcome to Dr. Diptiranjan Sahu. Sir, please. It is over to you now, sir. Hello. Sir. Sir, please unmute. Sir, please unmute you.
Yeah.
Yes, now it is okay.
Okay. Good afternoon. Have you listened to me?
Yes.
Yes, sir. Now it is audible.
Okay. So I can just a minute. Okay. I can. Have you seen my screen?
Yes, sir. Now it is me.
Okay. Okay. Good afternoon again. Thank you very much for giving me an opportunity to present some of the work we have done for long years, and it is my pleasure to present the work to you. So my talk is today for presentation room temperature multiferrite properties of rare earth substituted helium, gallium, and cerium bismuth ferrite ceramics. I have to discuss about the comparative study, how these materials can be used in different purposes and what are the different properties can change with respect to the different doping elements. So this is my university, the Namibia University of Science and Technology, and I work in Department of Natural and Applied Sciences, which is situated in Windhoek. For people who don't know about Windhoek, so where I am working, so this is the world map. So this is Namibia. So this is the Africa. From this is the country called the Namibia. From this country, I work in city called the Windhoek, and this Windhoek, this is Namibia University of Science and Technology. This is a science-based university, which is the science and engineering faculty. So where we work in natural and applied sciences. So this is the basic outline of my work. So I will present basic introduction about the ferroelectricity and ferromagnetism. Then I have to discuss about the scope of the spintronics. Then how we can do the spintronics without magnetism. Then become the multiferrite materials, how we prepare the material, the experimental finding and conclusions. So in AFM, I find that some of the students is there. So I'll start with a basic so that student can understand. And this is a long studied materials, and people will study these materials based on the ferroelectricity, ferromagnetism, spintronics, and some now in photovoltaics applications also. So basics is, so this is what is charge. Every people will know the charge is the fundamental property of matters that exhibit electrostatic attraction and repulsion in the presence of matters. So this is the positive charge, you can find the effect of positive charge, and this is the negative charge, you can find the effect of negative charge. But based on this, what is electron? So everyone knows the electrons is the negative charge with negative charge and it is spin half. So this is the charge and the spin, so the electrons is behaves like this way. But how the people see the electrons? So electrons seen by electrician, so he's see that the only the electronics is the manipulation of electrons by using the charge for storage and processing information. So in this case, the electronicians almost completely neglected about the spin. So based on the electronic charge, they will consider the electric dipoles. So electric dipoles can give you the electrolyte, and you can observe the polarization behavior in a material. So based on the polarization behaviors, these ferroelectric materials are evolved. In case of these ferroelectric materials, this is the ferroelectric loops, looks like this way, and people understand the origin of the ferroelectricity based on the inversion symmetry and presence of the transition metal oxide with T0 configurations. And this is the ferroelectrics, which is a time reversal invariant, spatial inversions, and application is sensors and ferroelectric FEROM. So therefore, the ferroelectric crystals that exhibits the electric dipole moments, even in the absence of an electric field, and ferroelectric states the center of positive charge of the crystal does not coincide with the negative. So based on this, people study the ferroelectric materials and apply in different applications. And most important is the effect of pooling in the ferroelectric property. That means if the polycrystalline ferroelectric is there, it is a random orientation of the grains before and after pooling, and many domains also are present in a pooled materials which has a remnant polarization is non-zero. So based on this, individual electric charge can affect different directions, and you can get a ferroelectric materials with electric polarization and understand the polarizing properties. So this is the general scope of a ferroelectric sheet. So the memory devices and ferroelectric random access memory, but this is the limitation of a large consumptions in the volatiles. Now, if you see about a charged electrons seen by a magneticians, so if they are charged, so this is the purpose of the magnetism, which develops a materials in which electrons spin tend to align the parallel to each other, so it can observe like a magnet. So in this case, the charge of the electrons plays the secondary role. So magneticians observe it is on the spin behavior of the material. So based on this, they understand the origin of the magnetic moments, which comes from the electrons orbiting the nucleus, which is the center of the spin, and you can get the magnetic moment due to the orbitals and the spin behaviors. So this fundamental property is the Bohr magnetons, and they consider the orbital magnetic moments contributes to the magnetic quantum numbers. So based on this, that people understand the ferroelectric materials. So this is the hysteresis loop of a ferroelectric materials. So in this case also transition metal oxides with a partially deep filled metals, they understand the time reversal and spatial reversal inherent and ferroelectric materials show spontaneous polarization even absence of the electric field. So based on that, electrons, charge and the spin, people understand the ferroelectric and ferromagnetic behavior. So therefore, the ferromagnetism can seen in a rare earth elements with a long range ordering phenomenon, and it causes the unpaired electrons spin to line up parallel with each other in a region called the domain. So based on the domains, the properties of the magnetic materials can be understood. And small externally imposed magnetic field can cause the magnetic domains to each other and materials can be magnetic. So based on this, the magnetism can be understood. But basics, the Maxwell's equations can gives you how the dynamics of the electric field and magnetic field and electric charge can be the primary basic for manipulating and tailoring the exotic new properties. So if you tailor the materials by the electric field, magnetic field and electric charge, we can get a new exotic property of the materials and we can develop the new materials. So these are the fundamental Maxwell equation, the Gauss law for electrostatics, Gauss law for magnetisms, and Faraday law for electromagnetic inductions, and the Ampere's circuital law. So based on this, we can get the different form of the law, and we can get the different law, how the different law can give the specific physical significance. That means we can electrostatics, we can understand the charge from the field. You can understand the magnetic field with the no magnetic charge, and electric field from the time-varying magnetic field, and magnetic field from the circulate electric current. So different behaviors can be understood if you understand properly the Maxwell equations. So based on this, the Spintronics is developed. So the conventional Spintronics is the semiconductor Spintronics, where we can get that based on the imbalance between the up and spin down population of electrons and the holes created by the injection of spin polarized charge carriers. Ferromagnetic people understand the semiconductor Spintronics. But alternatively, we can build a device from ferromagnetic semiconductors that have an intrinsic spin imbalance. That means we can develop the source gate or drain gate structure, we can get the spin gate structures. But new question is magnetism is essential to manipulate the spin structure and current? So this is the questions evolved about the scientists, but these are the reported, they said they may not, magnetism may not essential to manipulate the spin and the structure. So therefore, there is a possibility that magnetism can be, Spintronics can be understood without magnetism. We can rely on the physicist ability to manipulate the carrier spin in semiconductor through spin orbit interactions. We can manipulate the spin through spin orbit interaction. So at microscopic level, one can intrinsically induce magnetic field through spin orbit interaction. So therefore, novel approach for material physicists to hunt a new materials to get similar behavior like this GMR, CMR, GMC only by electric field. So if by electric field, if we change the spin orbit interaction, or you can manipulate the spin orbit interaction, which you can understand the magnetism in a materials. So we can observe Spintronics in a magnetic, Spintronics without magnetism. So this is the possibility how it can be possible without the magnetism. So this is the possibility that if an electron is moving through a lattice, then if there is external electric field along with that atomic force is the Lorentz transform into magnetic field that act upon the spin of electrons. Using this type of interaction for manipulating the spin electronics obviates the design of a complexity which are associated with incorporating local magnetic field into device architectures. So if you do these things, then we can observe the magnetism without magnetism. So based on this, now I can introduce about this is the multiferric materials, how you can manipulate the ferroelectrics and ferromagnetism in this material. So this is the standard materials. Everyone will now people know about the multiferric materials, which is the thermodynamic potential energy content with magnetic and electric components. And these multiferric materials can show more than two types of the fundamental ferrocity. This is ferroelectricity, ferromagnetism, ferroelectric in the same material. So by the spin and the charge, we can manipulate these materials and we can understand different behaviors of this material. So this is the ferroelectrics, this is multiferroics, this is the magnetic behaviors of the charge and electric field. We can understand the ferroelectric, and by magnetic field and the spin, we can understand the magnetic behavior. So these are the possible applications of a multiferroic materials, which are tremendous applications in emerging fields such as spintronics, sensors, microelectronics, electric field control, ferromagnetic resonance devices, transducer with magnetically modulated devices. Now these are the most scope or more studied materials in different applications like post-state memory applications, magnetic tunnel junctions, telecommunication and security purpose. People also using these materials. So this is the scope of these materials. That means how the memory devices can be used and how the magnetic materials can be change this properties. So magnetic materials, you can use a non-volatile but information management. By memory devices, it can be replaced by ferromagnetic random memory. So that based on this multiferrous materials, we can reduce the low consumption and high speed, lower storage, and it becomes fast information management, low energy consumption, and non-volatile information storage. But this is generally known. There is so many few multiferroics is there, insulator versus metallics, and there is a d orbital status. So perhaps ion with partially filled d orbitals are simply too large to move away these behaviors. So generally, these are the two types of the multiferroic materials based on the origin of ferroelectricity and magnetism. Multiferroic materials are divided into two types. One is type 1 and type 2. So this is a type 1 is bismuth ferrites is studied materials, and this is the manganites, the GD or holmium of manganites materials. But how can you produce a new multiferroic materials based on this type 1 and type 2 materials? So therefore, in this work, the objectives of this work is to prepare impurity-free room temperature multiferroics for possibility of spintronics applications. So we select suitable substitutes or the dopants of the rare earth into the parent BAFO systems in order to study this structural, electrical, magnetic, and transport properties so that this can be useful for the applications. So why you choose the bismuth ferrite? This is a well-known materials which is a AB3 and the lead-free environment-friendly material. This is the perovskite structures, and this is a antiferromagnetic and a ferroelectrics, and it is a rhombohedral with a space group of R3C with a lattice parameter 3.965. And these materials can be used as a multiferrous material and well-known studied materials. But in this case, there is a basis for choosing these materials as a potential multiferrous materials for spintronics applications because it has a own potential ability to show room temperature electric polarization and magnetization, and it can provide additional degrees of freedom in device design and application. So this is the beauty of these materials, and having the option of synthesized bulk ceramics by varying or substituting rare earth and transition metal for enhancement of the multiferrous materials. And all the small polarization value is reported in BFM sterile, but first principle studies show that it can give you the more or the higher polarization, remnant polarization value, and it is sensitive to the materials processing. So if you process the materials in proper way, then these materials can be used for the device applications. But only the problem associated with these materials is this is a pure synthesis of pure phase bismuth ferrite is difficult, which can consist of the different impurity phases, and it is difficult to obtain a ferroelectric characteristic of bulk bismuth ferrites because of its large leakage current. So due to the formation of oxygen vacancy and create of a deep trap energy levels in the band occupied with the mobiles. And there is an inhomogeneous magnetic spin structure with a periodicity of long wavelength in commensurate spiral modulation resulting in vanishing nonlinear magnetic property. So if we overcome these problems with respect to certain behaviors, then we can use this for spintronics applications. So this is the experimental work, the simple experimental work. The synthesis process is based on the solid-state reaction. I am just representing about the bulk behavior of this material. So we have to repeat quenching and grinding. We have to process these materials, then form a pellets of the prepared materials and sinter at 850 degrees for 12 hours. Then we have to sinter it again more hours to get the materials and characterize these materials using different characterization technique for the structural, magnetic, and electric behaviors. But in this process, we use a method of called the slow step sintering schedule method to get a pure phase this material. So this is the process, sintering time and sintering temperature, where we can get us first we soak the materials for 4 hours, then again 4 hours, then we sinter continuous for 24 hours to get the property. And why we use this thing, we trial and error methods to get the pure phase bismuth ferrite materials with different long hours, and we prepare the materials with a higher temperature, then we have to confirm the higher hours, and finally we get this is the suitable temperature and the hours to get a processed materials with a different properties. And so in this paper, in this talk, I will report the 4 materials like a pure BFO and galvanum doped BFO, holmium doped, and cerium doped Bismuth. And this is the materials I reported here. This is bismuth 1 plus X, RX, and Fe. This is the bismuth rich ferrite, where we can use X equal to, for this materials, X equal to 0.1. We have prepared different set of the materials like bismuth deficient, bismuth rich, iron deficient, and other materials. Based on the best results, we see that if the bismuth rich materials is taken and studied, this material, it will give the interesting and more useful properties. And in this case, why we use the 3 materials like gadmium, holmium, and the cerium? Because gadmium interaction, we anticipate that anticipating the magnetic contribution of the d orbital in a rare earth element in BFO system. So d element means 5d rare earth is there. So gallium in the oxide form can suppress the spiral spin structure, and it can give the anticipating or the more good magnetic behaviors. Then in case of a holmium, we choose the holmium ionic radius is 1.05 and bismuth is +3. Then it can produce some structural disorder, and it can suppress the oxygen vacancy. So it is a lanthanide series, so it can give you the more interesting property. Then we choose a cerium doped materials, and the cerium, the ionic radius is 1.18 angstrom and the bismuth is 1.20 angstrom. So it can stabilize the oxygen octahedron in a better way and decrease the bismuth volatilization due to the high chemical stability. So it can affect the ferroelectric property. So therefore, with these 3 sets of samples is chosen to understand how this can be affect the magnetic, ferroelectric, and the electrical property of the materials. Further, why we choose the 850 degrees centigrade for 25 hours? Because we see that there's a report that 820 there's the impurity phases are coming in a BFO. But if we go to 880 degrees centigrade, then there's a multiple phase BFO is present. But if we therefore we choose the intermediate between 820 and 880, which is 850, to get the good pure material. So we choose a 850, and we trial with different hours of the sintering, and we see that about 25 hours sintering, we get a phase pure materials. Further, why the bismuth rich is there? Because bismuth rich, so if you heat the materials at 850, there is maybe the bismuth loss takes place. So bismuth loss due to high sintering above the melting point of the bismuth, which is 817. So it can suppress the impurity phase. So therefore we choose a bismuth rich. So based on this, we sinter the materials and study the properties. So this is the comparison study of the 3 materials. You can see the BFO, holmium doped BFO, cerium BFO, and GD BFO. So from this XRD, you can see that holmium still maintain the rhombohedral structures, but cerium and gallium change the structure because this is a suppression of 006 and it's the evolution of 1 to 1. 1 to 1 is there. So therefore, it changes from rhombohedral to the orthorhombic phase. In case of a pure BFO, you can see this is a rhombohedral, which has a multiple of the impurity phases is there, which is in the form of a B25, FO3, Bi2, FO4. So different impurity phases is there. But when you dope with the holmium 0.1, impurity phase is gone, but it still maintains the rhombohedral structure, which may reduce the interatomic band structure related to holmium with respect to the iron and the oxygen. But when you go to the cerium and the gadolinium, we can see that the impurity phase are suppressed and the new phase is there, and we get a orthorhombic structures. So this one, the detailed XRD study is done based on the different analysis, and we find that the structural distortion takes place in a gadolinium and the GE materials instead of a holmium material. So in order to understand the SEM, we have to again study about the SEM scanning electron microscope structure of the BFO, the doped and the BFO structure. So in this case, you can see that the irregular shape, different shape of the grain ranging from micron to the millimeter shape size is observed. And here you can see this is the gadolinium dope and this is the cerium dope. So these two structures looks like the same of the different grain size, but in case of a holmium dope, you can see this is the individual grains are stuck with each other. So when they are stuck with each other, they form a laminar or columnar structure. But in this case, we can get a different grain structure. So grain growth junctions from few nanometers, which helps the percolating intergrain growth transport current. So which can inhibit the leakage current, and it can improve the electric polarizations. So if you individually, if you see the one like SEM of a gadolinium or BFO, here you can see the in this case the GDM is definitely helping the control of the microstructure, which shows the orthorhombic grain growth fabrications and the clear cut grain image. So this will affect the structure of the materials. Then you understand the leakage behavior or GB characteristic of this different compounds. So in this case, you can see the leakage current as a function of the forward and reverse bias of plus minus of 20 volt to study these materials. We can see that we have symmetric loop around the current axis, and leakage current is reduced significantly up to 10 to the power up to the fourth order of magnitude in case of a all sample. So therefore it can be promising, all are promising for the multiplex application. So that means that if you sinter the materials with a slow sintering process, there is a suppression of vacancies there, which can give you the leakage current improvements. So then we can study this one, how the conduction behavior or the transport behaviors with respect to log G and log E, and where we can get the leakage current short ohmic behavior up to certain range, and there is a like a space charge limitation which can give you the information of the conduction mechanism of these samples. Then we understand how the dielectric behaviors or the dielectric properties of these materials can be affected with respect to the different behaviors. So in this case, you can see that with respect to the materials, it is the frequency dependent dielectric behaviors. So frequency dependent dielectric behaviors of the all samples, and this is the loss tangent and this is the dielectric constant with respect to certain frequency range. After certain frequency, then this one dielectric constant is changes abruptly. Sorry. So that means in this case, you also observe that, that means the dielectric constant and loss is a frequency dependent, and in this case for the gadolinium there is a high dipole moments due to the structural distortions, and polarization becomes contributing the dielectric constant. So in this case, if you understand the polarization behavior from this dielectric measurement, then you can see the dipolar and interfacial polarizations which can affect the grain boundary. So due to this grain boundary, local defect or the local charge density can changes the dielectric behaviors. Then we understand about the CV characteristic or the CV capacitance and voltage behavior of this material. So we can see that in this case, it is likely caused due to the increase of the conductance there, and it can increase the conduction behavior. And in case of holmium, it is reduced, which is due to the movable charge is reduced, so that therefore it becomes the CV characteristic is reduced. Then we understand about the PE measurement or PE behaviors or PE, the polarization and electric behavior of these materials, where you can see that. So in this case, the all will give instead of a BFF against BFO, this all will give a specific polarization loop. So from this polarization loop, we can understand that. So in this case, you can see the polarization value is about 11, and in this case, it becomes 13, and it's up to a positive up to 15 microcoulomb per meter square. So that means polarization it changes, and you can observe the contribution of the bismuth rich ions for enhanced ferroelectric properties. So in the case of a holmium, there is a suppression of the oxygen vacancy which can decrease the leakage current, and in this case there is a movable charge which can significantly reduce the holmium substitution, so that we will observe a perfect polarization loop. So in this case, you can understand that there is a local microscopic distortion which can take place in these materials in the unit cells, which can without changing the space group, and which can get a specifically ferroelectric behaviors or the ferroelectric loop in these materials. Then we understand about the magnetic behavior. So in this case, BFO you can get, this is the magnetic loop, but in cerium and holmium we can get a perfectly MH loop, but in case of iridium, this looks like a leaky behavior type of the loop. So in this case, the defect structure or defect driven, so this is like a defect structure or defect driven magnetism, which can suppress the spin structure. We can observe MH loop like this, but in cerium, it is like saturated there, but in case of holmium, it is like a linear behavior. So you cannot, it is not saturated, so it gives the more ferroelectric behavior. So in this case, the magnetic interactions between the iron Fe3 and Fe plus rather than the spin can contribute the magnetic behavior. So therefore, there's the enlargement of the magnetic behaviors, magnetic loop is there. So this one understand, if we understand the empty behavior of a holmium material, we can see that there is a signature of the spin glass behavior in it low temperatures, and the suppression of the spin modulation takes place in this material. So that positively gives the specific the higher ferroelectric behavior. So in this way, we study the structural, magnetic, electrical behaviors of the materials. So based on the different applications and different measurement, we can get which materials can be used for different applications. So in summary, I can summarize the work. That means we can produce the impurity-free monopoly high-density BFO ceramics by suitable variation of the metal ion concentrations, and we can observe a well-saturated ferroelectric loops, and magnetic behavior of the sample can be improved significantly when rare earth ions are incorporated in BFO systems, and leakage current can be suppressed due to the absence of the oxygen vacancy and impurity phases in the doped materials. Finally, these are my reference and publication based on this work. These are the different publications with the different collaborators. So finally, I will acknowledge, that means this is my research collaborators and contributors from different regions of the regions, and these are the institutes or the which have a funding agency which can contribute the research work in different regions. So finally, thank you for your for the presentation.
Thank you, sir. Thank you, sir.
And this is the last thing I can. Okay, this is the last thing I can say. So there is a book project on this multiferrics for photovoltaic applications. So this is the editor is I myself. So in this work, if anyone interested can submit his contributed chapters on the books, and happy to handle this submission. And for this book chapter and book, so there is no publication charge. It will funded by someone, and the due date is this times. So thank you for your attention.
Thank you. Thank you once again for giving this nice, informative, and this encouraging presentation. So now this is time for questions and discussion. And we have a couple of questions here, sir. Let me read out here. So one question from Provin Paliwal. On which system P loops is recorded? What was the thickness of samples and the strength of voltage applied?
So in this case, these are not
Sir?
the thick sample, these are bulk sample, not the thin film sample. So thickness is not known. This is the bulk sample. So we prepare by a solid state reaction method. So, but for the if you prepare the thin film sample, so different thickness gives you different shape of the loops.
Okay, sir. One more question from Arun Kumar. How you have controlled the bismuth loss during the synthesis of pure BiFeO3 as it evaporate at 850 degrees Celsius?
Yeah, therefore we choose a bismuth rich material. So we have to change the composition, different composition. So we do trial and error method. So different samples are prepared, but finally we see that if you take a bismuth like the sample is 1x, that means if we add more bismuth to the system, so there may be loss is less. So we measure it by, we do XPS, we do XRD, and some EDS. So different measurements are done. Then we can contribute that if the bismuth rich materials is there, then it can contribute to not the bismuth loss can be minimized. So this is based on the how you prepare the sample and different process of sintering.
Okay, so one more question from P. Mitra sir. What is the temperature at which the dielectric data taken, RT or something other?
Room temperature, I think this all are reported is the room temperature. These are room temperatures, all are reported. But we have do it with the temperature variations, frequency variation, low temperature also there.
Okay, so one more question from Saurabh. What are the phases and the crystalline structure when rare earth metals are brought?
What?
What are the phases and crystalline structure when rare earth metals are brought?
In this case, this is a rhombohedral and it changes to the orthorhombic system. So these are the different analysis, this is the rhombohedral structure is there. So based on the lattice parameters and the structural transformations analysis, ritual analysis, we consider this is the rhombohedral and it changes to the orthorhombic system. So if you drop the different materials, it becomes orthorhombic. But pure phase is a rhombohedral and holmium also maintain the rhombohedral structures.
Okay, sir. One more last question, sir. What could be the reason for low value of experimental polarization, while theoretically it has around 100 micro per cm?
Can you tell again?
What could be the reason for low value of experimental polarization, while theoretically it has around 100 micro cubic per cm?
Because bismuth has a high leakage current, so leakage value is there. So we try to improve it with respect to the theoretical value. Theoretically, it is predicted is about 90 to 100, but experimentally for a bulk material, it is difficult to reach this thing. So how you can improve this leakage current value? Therefore, we try to increase it. Like from BFO, you can see it about 5 to 8 maximum, but we have to increase up to 15. So based on the different doping materials, we can try to improve this leakage current. So this is due to the different leakage behavior, oxygen vacancy, spiral structure. So different properties can contribute, different behavior can contribute, which can reduce the leakage polarization value.
Okay, so let's thanks our honorable speaker. Though lots of more number of questions are there, our speaker can directly contact or we will provide the email ID or contact number of our honorable speaker so that you can clarify and the rest of questions can be communicated through your email. Thank you, sir. Let's thanks our honorable speaker, Dr. Defect Sahu. Okay, so thank you, sir.
Okay, thank you again.
Thank you, Deputy Sahu.
Okay, thank you.
Very nice presentation, and I hope when you will visit India, definitely visit KIIT University.
Okay, thank you very much for the invitation. Okay.
And you have finished and in last moment you have selected it and giving very nice presentation. And another talk we have Professor Emre Adam, already he joined. So
Okay. Okay, thank you very much.
Adam, you have joined? Yes. So Bidu Bhushan, you can already Emre joined. So nice to see you, Emre.
Hello, Parashar.
So
Nice to see
I request
you also.
Bidu Bhushan Sahu to chair this session.
Okay, so thank you, sir, once again, Dr. S.K. Parashar, sir, for giving me this opportunity to chair this session. Again, so now we welcome you all to AFM, that is the Associate Professor of Savans University. Sir, welcome you once again to AFM 2020. Now, it is a great pleasure for me to introduce who is now professor at Savans University, Faculty of Engineering, Natural Sciences, Material Science and Nano Engineering Program, Istanbul, Turkey. He obtained his degree from Ankara University, Physics Department in 1998. In 2001 and 2006, he received his MSc and PhD degree from University of Leipzig Physics Department, respectively. He did postdoctoral research at the Technical University of Darmstadt between the year 2006 to 2009. In 2010, he became a researcher group leader in the Institute of Physical Chemistry at the University of Fribourg on the spectroscopy studies of functional nanomaterials. He has a strong background in diverse fields such as material physics and chemistry, physical chemistry, atomic physics, solid state physics, defect chemistry, studies on electronic properties of energy materials, and thus his synthesis, characterization of nanocrystals like your functional nanomaterials, piezoelectrics, supercapacitors, and particular semiconductor quantum dots. He was awarded a studium that is Marie Curie Research Fellowship in 2017. Again, Grand Prize in 2011 and third fellowship in 1999. He authored, to his credit, he published more than 74 publications in international journals and more than 50 invited talks in conferences. And one more very important, that is, he's the editor-in-chief of the journal Experimental Results and also associate editor in scientific reports. So once again, sir, welcome to AFM 2020 Department of Physics, KIIT University. So now it is, now I hand over to you now, sir. Please continue your time. Thank you, sir.
Yes, thank you very much, Sahu, for this introduction. Thank you very much. I would like to thank, first of all, I would like to ask if my voice is coming properly.
Yes,
is it okay?
sir. Yes, sir, it is audible, sir, clear.
Okay. So first of all, I would like to thank the organizers. It's a very nice webinar, but special thanks goes to Parashar for invitation. I know Parashar since 2006. We worked together in Technical University of Darmstadt in Germany, and we did a good job there, and we had plenty of publications with him. So it is a long time ago, Parashar, so I'm very happy to see you again, and I'm very happy to be here. Today I will talk about point defects, but especially detection of point defects with spectroscopic techniques, especially EPR spectroscopy. So EPR spectroscopy is not very common in material science. Therefore, I will give a very introductive seminar. Most of you probably knows all these things, but I will only sum up and give small details or small hints how to get a reliable defect structural model by the aid of EPR spectroscopy and by the complementary methods such as photoluminescence, Raman spectroscopy, etc. So let me start with the basics of EPR spectroscopy. This will be the first part of the talk. And then I will give two important prototype material. One is ferroelectric, lead titanate, and the other one is zinc oxide, which is a semiconductor. These two are probably the most common prototype material for ferroelectric and for semiconductor. So if we understand how to treat these two materials, then one can go further for the fancy materials like lead-free ferroelectrics or lead-free piezoelectrics or any other composite of semiconductors, etc. Let me give you a brief introduction to EPR spectroscopy. You know, EPR spectroscopy is mainly working with the microwave radiation. So you first need a microwave radiation, which is in the region of gigahertz. So this is a typical spectrometer. You have a light, you have a sample, and you have a detector. But in EPR spectroscopy, you have an additional magnet. That's the most important part of EPR spectroscopy, and your source is possibly Gandiet or klystron. So if your magnet energy and your light energy, radiation energy is equal to each other, the system goes to resonance. That's why it's paramagnetic resonance spectroscopy. So we need unpaired electron or spins. Basically, in material science, we use these unpaired electrons or spins as reporter. This spin gives us an information about the environment of the material, local configurational environment. So this is highly local. Sometimes it is first Legend sphere, therefore it is microscopic information. So you can gain microscopic information from the EPR spectroscopy, the site or the atomic environment or the symmetry, bonds, etc., or dynamics. You can get lots of information from the EPR spectroscopy in material science especially. And you really need a less sample, around 100 microgram or milligram, and you can measure as much as you can. So this is a non-destructive method. And as you see, the concentration, the sensitivity is very, very high compared to NMR, for instance, because detection of nucleus is much difficult than detection of electrons. Therefore, the sensitivity is much higher in EPR spectroscopy compared to NMR spectroscopy. So here are some, these are the pictures from Freiburg University where I worked more than 10 years that I used almost all of them. So you see there are different magnets here. And these magnets are depending on your requirements. You go different spectrometer to different spectrometer. You go to the higher fields. You go to the higher frequencies accordingly. Why do we need high frequencies? Why do we need high magnets? Because sometimes you cannot resolve anisotropies in your sample system. Therefore, you need to go to the higher fields, up to 30 Tesla. So a standard X-band EPR spectrometer has 0 to 2 Tesla magnetic fields. These are electromagnets. And if you go to the higher magnetic fields, then you should make the system from the superconducting magnets. It works very simple. You have microwave source. The microwave comes from here and go to the middle of the sample, middle of the magnet, and the sample is in the middle of the magnet. And as I said, when your microwave energy is equal to the magnet energy, which is called Zeeman splitting energy, Then you will get the resonance, and then you will have a detection of your signal at the resonance. And for each sample system, depending on if you have powder, if you have single crystal, if you have liquid, if you have thin film, your sample holder, which is, we call it resonator, may be different. If you have a high dielectric sample, your cavity can be different. Therefore, EPR research is highly expensive because each of these resonators are highly expensive. But nowadays, Bruker made a new type of new generation EPR spectrometer that we have now in our lab, that is a benchtop EPR spectrometer, which is able to measure under UV radiation. You can make a angular dependent EPR measurements and at liquid nitrogen measurements. So it is all in spectrometer compared to these ones. Okay, it has some limitations, but it works very well for doing a standard EPR research. So paramagnetism is important. Paramagnetism means that all these magnetic dipoles under strong magnetic field align to the direction of the magnetic field. So these materials are called paramagnetic, and they are EPR active. If you have a paramagnetic system, you will be able to measure EPR signal from these sample systems. So in physics, if you have a degenerated state where the electron sits in the ground state, and if you apply a magnetic field, there will be a splitting under magnetic field, which we call it Zeeman splitting. And this Zeeman splitting, as you see here, the population difference. And once you apply the microwave energy, then you will get the resonance condition. And from this condition, you can get the free electron G value. Okay. I see some people want to ask some question, or I don't know, but let us leave your questions at the end of the seminar. So then you have a first derivative EPR signals. If you see here, there are some, this is a first derivative. Normally it is an absorption, but for the sensitivity reasons, in general, EPR signals are presented in first derivative format, because you can easily see here the upper part and the down part may show some broadening, inhomogeneous broadening, so that you can see such broadenings or asymmetry in the line shape. Therefore, it is much easier to show the spectra in first derivative. Also, the G factor can be determined much easier than this one. Basically, everything in material science is physics and interactions. So if we have a magnetic field here, and when the electron spins are interact with the magnetic field, you get the electron Zeeman term. When the nuclear spins are interacting with the magnetic field, you get the nuclear Zeeman term, which is indeed NMR. And the electron spins can interact with the nuclear spins, and this is the hyperfine, which is independent of the magnetic field. Very interesting. And then finally, electron spins can interact with each other. This is spin-spin interaction. This will give us a fine structure parameter. And then the nuclear spins can also interact with each other. And this is called nuclear quadruple terms. This one can also again determine by NMR spectroscopy. And then I can construct my spin Hamiltonian. And then these red parameters, G factor, hyperfine, zero field splitting parameter, and quadruple terms can be determined directly from the EPR spectra. So there is no any method that you can determine these parameters experimentally directly from any other spectroscopic technique. So EPR is, in terms of spin Hamiltonian parameters, very, very powerful. So as you see here, these are the energy contributions. Electron Zeeman is the highest energy contribution. Then comes, so here is the magnetic number you see here. They all give some contribution to the system, and then finally you can get directly these contributions as an hyperfine or fine structure parameter. And if you have a high spin system, for instance, systems that are doped with metal ions, general metal ions like manganese 2+, chromium 3+, gadolinium 3+, they're all high spin systems. And these high spin systems has electron spin 1/2, larger than 1/2. And they have zero field splitting. This is generally called crystal field splitting as well. That means before I am doing EPR experiment, I have splitting, okay? Crystal field splitting. And that crystal field splitting is defined as D parameter, as you see here. And that D parameter can be determined directly also from the EPR experiment. And depending on if the system is in octahedral field or tetrahedral field, then the electron spin number will be changed because of Legend field theory or crystal field theory. You all know this in physical chemistry lectures. Therefore, depending on your high spin or low spin system, you can again get the information about the crystal field parameter. For instance, very interesting example. Let's say you have a crystal in an octahedral field. One is high crystal field, the other one is low crystal field. And if you have a small crystal field, as you see here for S = 5/2 system, I can resolve all these electronic transitions which are allowed. So I have 5 lines. But if I have a large crystal field compared to Zeeman, then I can only resolve the central transition. Then I get an effective G factor. So I cannot resolve these electronic transitions. That's why people in EPR spectroscopy invent or go to the higher magnetic fields to resolve these electronic states as well. And for this, a standard X-band EPR spectrometer is satisfactory or enough for getting all these electronic transitions. So that is how crystal field is important for EPR measurements. These are the real examples now. I just want to show you, for instance, zinc oxide compared to lead titanate has a lower crystal field. Generally, perovskites has a high crystal field in gigahertz order. But zinc oxide is a semiconductor. It has a zero field splitting crystal field in megahertz. So it's a huge difference. And as you see here, when I do, for instance, manganese 2+ zinc oxide, I can resolve almost all of these transitions, including hyperfine. But in lead titanate, which is compared to Zeeman, it's too high. It is in gigahertz crystal field. As you see here, I only observe one single line, which is an effective G factor. Indeed, iron 3+ and manganese 2+ here has the same electron spin number, which is 5/2. So I always expect 5 lines from both. But here in zinc oxide, I observe them 1, 2, 3, 4, and 5. And additionally, hyperfine, 6 hyperfine, 6 times 5, I observe 30 lines. So I can resolve all these interactions because the crystal field is too low. But here not. I cannot resolve any EPR transition here. Also, to go to the higher magnetic fields is important because sometimes the G anisotropy, you see G is a matrix or a tensor, therefore there can be anisotropy in the G factor and normal standard EPR spectrometers sometimes cannot resolve this anisotropy. Therefore, you need to go to the higher magnetic fields to resolve these anisotropies. And this is an axial, this is an isotropic, this is an axial, and this is a rhombic case. And as you see here, it's an example, this is just a simulation. And once you do the simulation in X band, Q band, so I'm increasing here the strength of the magnetic field, and as you see here, a nice anisotropic resolution is obtained in 406 gigahertz. And this 406 gigahertz is nowadays in a very, very rare exist in the world. One is in Tallahassee National High Field Magnetic Lab, and the other one is, I think, in Grenoble. What can we do other examples? For instance, here a solar cell. For instance, this is a silicon dioxide solar cell, and this is an EPR experiment. So we want to distinguish the defect centers in silicon dioxide, and these are the possible paramagnetic, this is important, paramagnetic defect centers, which are EPR active. There may be other defect centers which are not paramagnetic, but we are now dealing with the paramagnetic ones which gives an EPR signal. So once we measure it, we don't have any idea about this spectra. But with the help of the simulation, which is the physical simulation, that by giving some spin Hamiltonian parameters, I can determine such different centers. And when I add these three fit simulation, then I get such kind of total spectra, which is comparable with the experiment. So that means that I can identify three different centers, and I can also identify their concentration, because the area under these curves will give me the concentration values of the defect centers, so that I not only determine the centers, but also determine the concentration of these defect centers. Let me switch to ferroelectric oxide ceramics. We investigate in this small study the size effect. For instance, mostly the ferroelectric materials below 50 nanometer has a critical size. So you cannot go arbitrarily small particle size, otherwise you will lose your ferroelectric property. So you will have to maintain your ferroelectric property, and also you need to keep your particle size in nano range. That's the challenge. So this is a bulk lead titanate, and as you see here, the Curie temperature is well known, 766 Kelvin. And above this temperature, we have a Curie temperature, which is cubic. And below this temperature, the system is tetragonal. These things is well known. And in this case, the zero field splitting parameter is 0. That can be, or crystal field parameter is 0 in cubic phase, and this is non-zero. And we know that it is the first order phase transition in lead titanate. And the transition is displacive. These are well-known issues. Now, if you make lead titanate EPR, you will get no signal because it is diamagnetic. Therefore, I need to make it paramagnetic. The strategy is to add a small amount of doping ion, which can be copper, chrome, iron, gadolinium. You can add manganese as well, so you have a plenty of choice. We choose chromium 3+ because it has no hyperfine, because the nuclear abundance I = 0 is 90%. That means the nuclear interaction is 0. Therefore, it is a good choice. I don't want to deal with the hyperfine. So I will only determine the D parameter from the EPR spectroscopy and the G factor. And it has 3½ electron spin. Okay, this is a very nice synthesis part. Parashar knows very well these synthesis technique, which is called combined polymerization and pyrolysis. And afterwards, we apply some ball milling, and with mechanical, very little mechanical energy, we can go down to 15 nanometer. This is just synthesis part. Now, here you see some splittings. These are tetragonal splittings from 90 Kelvin up to 766 Kelvin. You see here a very nicely gradual divergence to a single line, which is an indication of a cubic phase. So these are the splittings gives you the D parameter, basically, which is the crystal field. And we draw this with respect to temperature, and there's a first order phase transition. So this is from the EPR. And basically, this is not a surprise, because in 1986, the spontaneous polarization versus temperature already give this value to us. So this is a first order phase transition. Nothing strange. Good, we invented the world again, but now what we do is, this is a temperature-driven phase transition. What we do is, we keep the temperature constant at room temperature, but we change the particle size from 200 nanometer to 6 nanometer. And as you see here, we observe a similar divergence of a signal to a single line indicating a cubic phase transition. That means now we have not temperature-driven phase transition, but we have a size-driven phase transition, and this we can observe by EPR spectroscopy. So you can also test this with different techniques. We can compare with the dielectric spectroscopy, and the maximum of the dielectric permittivity gives you the Curie temperature in dielectric spectroscopy, and the maximum of the intensity profiles also gives you the TC, and they all give similar behavior in different methods. This is EPR, this is dielectric. Finally, we can plot the XRD graph, the dielectric graph, and EPR in one plot, and we see that around 10 nanometer or around 6 nanometers, sorry, we have a strong deviation from the values, which is called size effect. That means this crystal field, the Curie temperature, and the tetragonality is reducing drastically. And 6 nanometer, it is disappear. That means we have a transition at 6 nanometer from ferroelectric phase to paraelectric phase. And this has been, after we published these results, the theoretical group in Ukraine did some Landau phenomenological theory calculations, and from that calculations they put these triangles. These are our data, lead titanate powder. This fit very well to their calculations, and they found 4.2 nanometer as a critical size. This was in 1994, and this experimental value is the closest up to now to this theoretical value. That was for us very nice surprise, and we very happy with that. Of course, you can make a test measurements for Raman, because the soft mode here is the fingerprint for the ferroelectricity, because the ferroelectricity is a long-range phenomena, and if you lose the long-range phenomena by reducing the particle size, then the short-range forces will be dominant, and this will be relax the soft mode. Therefore, we see this relaxation of soft mode around 6 nanometer. This is so this is another indication of critical size, which supports the EPR experiment. By EPR, you can also determine the site of your doping element by using crystal field theory. So there is a model which is called Newman superposition model. So this is the formula which correlates your EPR parameter, zero field splitting parameter. This can be obtained from EPR with the bond angles and bond distances and some intrinsic parameters. And if you make this calculation, and you will see that you will observe 3 different displacement of chromium ion by including oxygen vacancies, so you can determine if there is a vacancy in the first Lejeune sphere or not. So in this case, there is no oxygen vacancy in the first Lejeune sphere. So you can change the ion, for instance, from chromium to iron. And as you see here, this is in tetragonal phase, from 500 nanometer, purely tetragonal, and we reduce to 12 nanometer, we will have an additional signal here, which is an axial tetragonal phase. They are coexist in the middle ranges. And at around 12 nanometer, we have an additional signal here, which is in cubic phase. Therefore, you can also, by reducing the size, you can also determine the portion of your phases that you may not probably obtain this kind of analysis by X-ray diffraction, etc. And then you can make a model, core shell model. So you have here a tetragonal phase at large sample, which is a bulk, and only one tetragonal spectra. Sorry, yes, tetragonal spectra. And if you have some nano, then you will have interface, you have distorted phase, and you will have still tetragonal phase. Then you will have all three phases in one EPR spectra. And finally, if you go down to critical size, then you will get a cubic spectra, which is G equal 2. For instance, here, the PZT system, doped with iron 3+, this is morphotropic phase boundary, which is very, very popular to investigate this morphotropic phase boundary here, tetragonal and rhombic, etc. So what we did here is we gradually changed the stoichiometry of lead titanate and zirconium titanate. You see here PZT. In this case, zirconia is 0. In this case, lead is 0. So lead titanate and lead zirconium titanate. This is a typical rhombic. This is a typical axial. And then by changing this, we can monitor the difference of the spectra, which gives you this rhombohedral and tetragonal phase boundary. So this is another monitoring of phase transition in lead zirconium titanate phase. We have plenty of different fancy publications on KNN, BNT, BT, and bismuth sodium titanate. These are all ferroelectrics, etc. Now I would like to switch to semiconductors. This is more nice because I like this topic very much, because zinc oxide is diamagnetic, but it has intrinsic defects, so that is in nature become paramagnetic. So if you for lead titanate, we don't see anything, but for zinc oxide, because the band gap, it has a wide band gap, 3.4 electron volt, we can observe these intrinsic defects. But these intrinsic defects, like oxygen vacancies, zinc vacancies, these ions should be ionized. They should be paramagnetic, okay? So for instance, to observe the oxygen vacancy, that oxygen vacancy should be singly ionized. Otherwise, we can't see them. So by this, you can also add some iron, manganese, cobalt, and chromium metal ions as well. So this is just a similar synthesis of zinc oxide by ball milling. So we can go around 20 nanometer. Here, you see a size effect. Now it is different. So this is a bulk, one signal here, and 500 nanometer to 50 nanometer, we have an additional signal here, which is appeared. And finally, at 4 nanometer, that signal is removed. Only there is one signal left here at 2.004. So this is now, we don't know which signal is belong to which defect centers. This is the main challenge in zinc oxide. Okay, we know that these are from oxygen vacancies, these are from zinc vacancies or oxygen interstitials. But which signal is from which, we don't know. If you look at the literature, you can find lots of DFT calculations that are giving you some formation energy of defect centers. But how reliable are these calculations, and morphology is different. Maybe they do for single crystal, etc. And we have here powder. So they're all different. Therefore, considerable conflicts are present in literature. But we have one certain thing. It's the with the nano size, we have bulk, only one signal. These are the surface defects. Let's say in this volume, we have 100 defects. But here in nano, we increase the surface defects, amount of surface defects in the same volume. Therefore, we have here enhancement of surface defect so that it becomes visible. This is G equal 2, this is G equal 1.96. At least we safely separated surface defects and the core defects, okay? And now you can make a correlation between photoluminescence and EPR. So as I said, G equal 2 is the surface defects and G equal 1.96 is the bulk defects. But these are paramagnetic, only paramagnetic. But here in photoluminescence, this is a general mistake that people do. This is an electron-hole recombination, nothing related with the defects. That signal, which is visible, is related with the defects, but this one is bulk plus surface defects. So all defects are here possible. But here only paramagnetic defects are possible. And here I can distinguish surface and bulk, but here I can't distinguish surface and bulk. That's the thing, that's the challenge. Many people do these things, but there is a kind of misunderstanding, especially in photoluminescence. They generally give here the convolution, and because of this deconvolution, they say this is yellow emission, this is yellow emission, this is green emission, this is blue emission, and they generally combine this with DFT in literature, find one relevant DFT energy, and say this is oxygen interstitial. So this should be not the case. There are many different defect centers possible in zinc oxide, but we are aware that indeed that defect, which is a trap electron, is bounded in the core, and that one is more unbounded or relaxed in on the surface. That's why it is like a free electron value. So you can make a core and shell model analytically, and from this you can easily determine the thickness of the shell by this analytical calculation, so that if your thickness is 1 nanometer, you cannot determine that thickness by even high resolution transmission electron microscope. But with this effect center concentrations, you can identify your thickness, which is in this case 1 nanometer, and also you see here the defect concentration on the core and on the surface can be determined. You can apply a laser and see how these defect centers changes by or reacts with the light. Very interestingly, I did this experiment. I simply put a continuous wave laser in front of the magnet and sent a laser light to the system, and meanwhile in situ measure the intensity of the defect centers from the EPR spectra. And I applied 3 different light: blue, green, and red. And let's see what happened. So this is a surface, this is a core. And when I apply a blue light, which is 2.78 electron volt, and I see in this core defects, you see the intensity is enormously increased, and then at one time it saturates. Then I turn off the signal, it goes down. It's a very nice controllable system. But the surface defects has no controllability. They are somehow dancing electrons on the surface. So this is the blue light, which is high. So if I apply a green light, I see here a little bit systematic, but it goes down. And then some cycle, it goes again up and so on. So this is again really kind of controllable. Then I get bored from this measurement and I turn again to blue. And you see here again, it goes up very high. Then I go off, it goes down. And when I turn back to green again, it goes to these intensity levels, which is highly controllable. These core defects are really controllable defect centers. But you see here shell, it is independent of the light or independent of the laser light. So it gives all the same structure. And finally, if I go to the red, nothing changed. You see here, red is too low energy to activate the defect centers. And then it goes very high when I back again to blue light. So it's again controllable thing. And you can make a defect control by changing the stoichiometry. So you can make chemically oxygen-rich or zinc-rich system. This is in white or greenish. From the photo, it is not visible. But you see that by just adding more oxygen, it becomes red. And by adding more zinc, it becomes blue. So there's a blue shift and red shift by just controlling the stoichiometry. This is another interesting control of defect centers. Finally, you can have zinc oxide doping with metal ions. This is a very interesting thing because you can go from this to the spintronics. Because nowadays, if you add metal ions, zinc oxide may become ferromagnetic at room temperature. So this is a nowadays hot topic, and people are discussing this. If it is ferromagnetic, at the same time semiconductor, these are called diluted magnetic semiconductors. And these are important materials for spintronics that can be used in quantum computers. But the question is, you need a diluted magnetic. Diluted, what is diluted? This is a too much concentration. So that means there is only magnetization. And there is almost no metal ion. So this is semiconductor. That means we need diluted. Therefore, we need to control this metal ion doping. And one of the best way to control this concentration is EPR. For instance, if you have zinc oxide doped with manganese oxide, and get manganese 2+ in it, the manganese oxide has a strong Gaussian line. As you see here, above this concentration, a manganese oxide on grain boundaries start to visible here. That means above this concentration, you lose your dilution. That's why EPR is one of the way to control your DMS system. And then you can make ferrite, but I don't want to discuss this now. So nowadays we start to make supercapacitors from zinc oxide, and these defects and make extra charge pads for supercapacitors and increase the specific capacitance of the supercapacitor devices. So I designed a real supercapacitor devices, as you see here in the photograph, and then you see here very nice humps of cyclovoltammetry figures, and we have reached 500 milliampere hour per gram for specific capacity values. So we have here, for instance, the zinc oxide electrode with pull-off defects, and the counter electrode was 3D graphene foam, and there is a separator. So these are real devices that we have done. And recently we have a cover images in nanoscale, 2 cover images in 1 year. So we are very happy to publish these nice articles. And I would like to thank all of you for listening, and I will be happy if you have any questions, and thank you very much for listening.
Thank you, sir. Thank you, sir, for an enlightening and informative presentation on the right way to apply. So I would like to one more thing, sir, particularly your presence in this virtual seminar gives lots of value to us, sir. Okay, so now open to discussion, and a couple of questions are there. So should I read out from here, sir?
Yes, I'm waiting. Thank you.
Okay.
Thank you for the question.
Okay, sir. Sir, one more question from Shravani.
can EPR spectroscopy be employed to analyze defects in junction of a PN junction solar cell?
Yes, it is possible, especially it is good for them. But one has to be very careful there because you should, I mean, in solar cell, you can synthesize all these junctions sometimes one by one. Therefore, I would suggest to make all these investigations step by step, if possible, and not the whole system in once. But whenever you do something, go to EPR, measure, and add the another thing, another junction, and then measure, and so on. So even the substrates should be measured. Otherwise, at the end, if you measure the final solar cell, you will get a signal, and it would be probably not easy to distinguish p-type contribution, n-type contribution, etc. So I would suggest to make every step, every interface should be measured and then checked. And then afterwards, you may have better understanding of contributions.
Yes, sir. Thank you. One more question from Lexa Mitra, sir. How can FRET be applied here?
Would you please repeat?
How can FRET be applied here?
FRET. What is FRET?
FRET.
FRET. I don't know FRET. Actually, what can it be?
Okay, so later on we will discuss that. So one more question from Saurabh. What kind of perovskite property measurements can be performed by EPR?
You mean what kind of perovskite?
Perovskite property.
Perovskite property.
Yeah.
Yeah, you can apply, for instance, if you have a temperature-dependent EPR spectroscopy, you can check, if it is ferroelectric, for instance, you can check the hysteresis by the temperature. You will have a similar hysteresis curve that you obtain from electrical measurements. That will be similar. Also, you can determine, as I said, the crystal field parameters, so that you can determine the site symmetry of your perovskite, if it is tetragonal, if it is rhombic or cubic, so that you can easily define your oxygen vacancies or your interstitials. So these are important, valuable information that you can gain from EPR in perovskites.
Okay, okay, sir. One more question from Subrat. Whether G factor of zinc oxide using spin orbit coupling is contributing much?
Can you please repeat?
Okay, whether G factor of zinc oxide using spin orbit coupling is contributing much?
Oh, yes, I understand. Yes, of course. So basically, the one who asked this question knows EPR. That's a good thing. This is more or less physics. Of course, due to the strong spin orbit coupling of the bounded state electrons, this will get deviation from G equal 2 value. Okay, so that means that defects, which gives 1.96 G factor, has a strong spin orbit coupling contribution. And the surface defects, which gives G equal 2, they have less spin orbit coupling effect. So that's a good question.
Okay, sir. FRET, sir, stands for that participant sent his query. that FRET stands for Foster Resonance Energy Transfer.
Oh, okay, I understand. Yes, of course.
Okay,
No, yeah,
so,
I skipped that part. I just want to go this part shortly.
Okay. Okay, sir. One more comment from our previous speaker, Dr. Diptiranjan Sahu. So please
Yes.
comment on spin wave resonance in EPR spectra for multiferroic materials.
For molybdenum?
Because comment on spin wave resonance in EPR spectra for multiferroic materials.
Multiferroic,
And
yes.
two more lines are there. Line width, his comment is the line width is related with spin relaxation time and the spin photon relaxation. How is it to relate with rest to EPR signal in magnetic material? And
Yes.
spin interaction and spin lattice interaction using EPR signal. So please comment on this.
Mm-hmm. Yeah, this is also a very nice question. I did some multiferroic investigations, especially for bismuth ferrite. Investigated iron 3+ signal, and of course the line width and the EPR intensity is related with the magnetization, and this of course there is no direct relation. The relation is you observe from EPR the paramagnetic susceptibility. So if you convert this magnetic susceptibility, or if you correlate your magnetic susceptibility with your multiferroic behavior, that will be perfect. So how can you do this? You make a temperature dependent EPR, and then you have two kinds of paramagnetism. One is Pauli paramagnetism, the other one is Curie paramagnetism. One is temperature dependent, the other one is temperature independent. Therefore, if you observe such kind of paramagnetism and the paramagnetic susceptibility and convert this data to your magnetic results, that will be very informative for your multiferroic systems. Thank you very much for that question as well. But the problem is generally the spin relaxation and the lattice spin relaxation in solid state systems, they're very fast. So it's very, very difficult to observe, to determine the T1, T2 relaxation. Therefore, you need to go to the pulse techniques. But for pulse techniques, as I said, since the relaxation times are very, very short, it is very difficult to observe this kind of relaxation time. Just for the Foster resonance energy transfer, the previous question, of course, here you see in the image, you can see that that EPR can give you an information for these distances. If you have, for instance, here zinc oxide, and if you add one molecule here, which is, for instance, rhodamin 6b, something like that, so that you can, the one is acceptor, the other one is donor, so you can get the rate of the electron transfer and the distance of this acceptor donor donor case. So if you have this from the FRET, you may correlate these data with the surface defects and core defects by EPR. So it's just a complementary technique. Yeah. Any other question?
Okay, sir. Thank you. Sir, no more questions are there. Okay, sir. Let's thank our speaker. And with this, we hope that the new research scholars are able to seek a little guidance and imbibe something from your talk. Sir, thank you once again because your presence gives a lot of value, sir, to this virtual seminar. Thank you, sir.
Thank you. I see
now
lots of young...
Dr. Parasar, sir.
Thank you, Sahu. I see lots of young scientists here. I hope I was very, very broad and very general. I know most of you know these things, but I just want to clarify or make a summary on EPR spectroscopy and defects in material science.
Thank you, sir. It is very informative to apply in the right way, sir. Thank you.
Thank you.
Now it is over to Professor Prasad. Thank you.
Thank you very much, Emre. You have given very nice and the thought what you have think. This time we have organized keeping in mind the young researchers, and that the presentation what you did. Many of the young researchers, scholars who are doing the research or they are going to do the research, this kind of talk is very, very useful. And yesterday we have did the international workshop for the young researcher scholar, and definitely I hope in the future also, maybe during this lockdown or after lockdown, we can have such kind of talk so that the people, even though EPR is not people can get easily very difficult signal, because EPR like XRD other ACM people can get the result, but EPR result is not easy task to get. For a specific sample you have to prepare, a specific properties should be there, then it can get the some kind of signal. This is a very sophisticated you can say the testing for the defect study, very, very nice and atomic level study, you can say it. So it is a very wonderful talk, and definitely the young generation you are going to motivate and excited. Even I get excited, even though we learned many things from you in the Germany, but I get excited. I also get recharged, and definitely your talk, because this all the talk is going to YouTube live. So in future anybody can see in the YouTube. This is already YouTube live, so you feel happy.
Okay, very nice.
And that
very nice.
your student can or anybody can listen your talk. So very
Yeah,
nice, and hope after the this lockdown you can visit India.
I will.
So that we can do some more research work.
Yeah. Okay. Thank you very much for your good words. I would like to take one photograph, all of you. If you turn on your camera, I don't know, I will take one photograph as a memory of this event.
Okay.
So
stop. Okay, fine.
So I see 150 people here. Very nice. Okay. I just want to take a photo. Okay. Smile. Thank you. Okay. So I don't know
thank you.
if thank you very much.
So we have the professor now, Katiyar sir. Satyanan sir. Satprakash Sahu sir.
Yes.
Dr. Satprakash.
Yes.
Yes.
I can hear you.
I invite you to the next session to chair it, and we have the Professor Katiyar sir, renowned person in the field of ferroelectric. So let you can chair the session on behalf of our organizing committee also. We welcome Professor Katiyar to accept our invitation and ready to give the talk. Thank you, sir. I request Professor Satyaprakash to chair the session, please.
Thank you, Professor Prasad. It's a privilege to be chair this session. And as you know, this I have been hearing this various talk recently from yesterday onwards. It is this conference is a different kind that you have arranged. It's a wonderful arrangement, and you have make sure that people from various background can come and attend this talk. And I'm quite happy the way this talk is going forward. And then actually now I am going to introduce hello, Professor Katiyar is there? Hello?
He is there. He is there.
So, Professor Katiyar, am I audible?
Oh, he is perhaps disconnected. He was there, but now he is. We can wait for a couple of minutes.
Yeah, maybe somebody can contact him.
Can Professor Paras can probably send a message. He is not there right now.
Dr. Prakash.
Yes.
Dr. Prakash?
Yes, I'm trying to contact him also.
You see, he already joined because his time is scheduled to 6 p.m. So later we can have for 5 or 10 minute discussion because his time schedule is 6 p.m. So he'll definitely join because once he joined, right? So his time is supposed to 6 p.m. So that is the reason.
Okay, so
not there.
maybe so shall we wait for some time? Hello? Shall we wait for some time? Because anyway, he's not there.
डिस्कशन करने वाले थे हमको ये समझे
हेलो हेलो हेलो
कैमरे से बात करें क्या बोल देते हैं हाँ उनसे ना आप तो व्हाट्सएप कर लीजिए ना ठीक है ना ओके 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 सो एमरे को बोल दीजिए वी कैन टॉक एमरे एमरे कुछ बोलना चाहता है so what is your Emre thinking that this energy storage the challenges you are going to solve it by your some point defect because this it is very important DPR defect how it's going to contribute in the especially the energy storage challenges to increase the efficiency can you give some comment on Emre इसको बोल दीजिए ना उसको नहीं कर पा रहा है वो
Yeah, a very good question. I forget to turn on my microphone. Yes. So it's a very nice question. Of course, the storage systems, in particular batteries and supercapacitors, important. But they both have one advantage, one disadvantage. Batteries has high energy density but low power density. Supercapacitors has higher power density but low energy density. Now the challenge is how can we make high power and high energy density supercapacitors, so that maybe in the future that they can replace the batteries if possible, or at least take some portion of the batteries, some work for the batteries, from the batteries. Therefore, this is what we want to do with the material science, basically with nano and doping and some finding a synergy between metal oxide sample systems and the carbon materials. So these are the challenging stuff to produce superbat. I call it superbat because super battery. I take the supercapacitor super and battery bat, so superbat. So if we find a high capacity, high energy density, and high power density system, then that will be very, very, very good. But it's not that easy. So there are new types of elements or materials.
Okay, so
like
just to interrupt, the speaker has just joined.
Oh,
Next
perfect.
speaker.
Very nice. Good news.
We'll continue this.
Okay.
And they can complete.
So
yeah, my conclusion is, of course, if you work with metal oxides as an electrode, then you can't ignore the defect centers. And these defect centers, especially in surface, in grain boundaries, in core, wherever it is, play lots of information. Therefore, you can't ignore them, you must investigate. And these defect centers cannot be investigated by macroscopic characterization techniques. You can't make it with XRD, you can't make it with scanning electron microscope. You really need electronic information, local configurational information, and that can be done by NMR, EPR, XPS, and Raman. These are very important informative techniques, gives you real information on the, and you need them cordially. You need them all, you need all of them almost, because alone one characterization technique will not give you full story. Thank you for this question, Parashar.
So thank you, Emre. So, now Professor Katiyar joined. I request Satyaprakash sir to session this, chair the session, and I think
sir, we are not able to see your
Katiyar is
presentation.
trying to or what you can share the screen from here.
See, I have presentation here.
Yes, we can see you.
Share the screen.
We can see you.
Not presentation.
We can see your video.
Yeah. Yeah, here is in the bottom, it says share screen. Okay, and then this will stop. We want to continue. Yes.
Share the screen.
Yes, yes, done. Good. बढ़िया हो गया. आप थोड़ा screen की कर ये full screen कर दीजिए.
Full screen. What? This is not the presentation.
मतलब जो power
Share.
mode जो होता है.
Okay. Presentation, but I have to go to the share. Share.
No, हो गया.
I have here basic and advanced. Those are the two things.
वो शेयर कर लिया क्या
What do we do? It doesn't show me the menu. But menu. But I don't see. I see only. Is this individual slides? Don't know what slides.
We can see your slides, sir.
No, these are not slides. This is something else. No, this is not. This is what I see is not the slides. You know, this is what I'm trying to say. Let's say this one. If we just open up now I can see the slides.
Yes.
Okay, now I can see the slides. So now I can go to full screen. Can you see now? Yeah.
Yes.
Okay, great. This is it. I got it. Yeah. All right. Okay, let me minimize this one. Okay, all right, okay.
So welcome to all. So this is a great privilege for me to introduce a person like Professor Ramesh Katiyar, who is a pioneer in the field of multiferroid and ferroelectrics. And you will be particularly the young people who will be listening his talk. I'm sure that he will show that what actually he has contributed to the field of multiferroid. Nevertheless, he has he has made tremendous impact not only in the field of multiferroid. When it particularly, if I summarize everything in one word, it would be the energy material. You will see, you will evidence, you will see, witness today the material that he will be talking about, the full idea, because I was privileged to work with Professor Katiyar as a postdoc with him, and I have seen closely the way he approached towards the problem, and it is not only the basic fundamental understanding how to make those material to the application level, and that is what lies his specialty when it comes to material science and physics. And not taking much time of yours, I would just briefly describe Professor Katiyar. Professor Katiyar did his PhD from Indian Institute of Science, Bangalore, in 1968. Then after that, he moved as a postdoc to University of Edinburgh, UK. After that, he joined as an assistant professor in physics at the University of Southern California in 1971. Then he moved to Brazil and joined at the University of Campinas as a faculty there in 1985. After that, he again returned back to USA, and he finally settled at the University of Puerto Rico, San Juan. And he has made a beautiful lab over there, which is flourished by various kind of instrument and advanced characterization technique. And he has mentored many people around the world and who have gone there, and he had made their life, I mean, particularly making training them in very advanced state, and many people have benefited from his lab. Not taking, and he has also, because of his publication, you can see his publication, he has published more than 1,200 paper, and he has got something like 24,000 citation. And he is also a fellow of American Physical Society, Material Science Society, Electrochemical Society, also American Chemical Society. His contribution towards the ferroelectric is tremendous. So without not taking much time of him, and nevertheless, his contribution towards Indian science is also equally important, because if you see many of the premier institute over India, where you will see either one of his students or postdoc is being situated, that shows his passion towards how to improve the Indian science in particular. Nevertheless, he has also contributed directly or indirectly to grow the science in different parts of the world, but his immense contribution to us India is unparalleled. So with these words, I will welcome Professor Katiyar to deliver his talk. Thank you very much.
Yes. Should I go ahead and?
Yes, please. Yes.
Okay. Okay. The talk actually, today's talk is actually progress in designing novel single-phase room temperature multiferroics. I have added the word spec lab because all the work that I'll be reporting, most of that is done at a spec lab, which is what actually at the University of Puerto Rico that I am taking care of that. The contributors of this talk are indeed Professor James Scott, Ashok Kumar, Danilo Barinoevo, Nora Ortega, Dilson Sanchez, Shalini Kumari, Dhiren Pradhan, and Karunakar Mishra. And from outside this lab, the other contributors are Professor Srinivasan from Oakland University and Marty Gake from Queen University Belfast. This keynote presentation I'm actually dedicating to my 50-year friend, Professor James Scott, who recently expired on April 6th. It's very unfortunate. We had contribution of almost 50 years with each other, collaboration, and we have over 120 publications together as co-authors. Before moving further, I would like to give you an overview of the SPEC lab. It's actually an advanced materials research lab that I established in 1985 at the University of Puerto Rico. We are doing all kinds of activities, as Satya has just mentioned, that we are working on high-K materials. We're working at ferroelectric, multiferric tunnel junctions, photovoltaic devices, lithium-ion batteries, which is a very different field, but we have been working rigorously in this area, and that is one of our major work now. We have been working on resistive memories as well for devices and MIM capacitors, and also high energy density capacitors that we have developed actually from thin film technology of oxides basically. Okay, there are several talks I noticed in this meeting on multiferroics of different kind of materials. And so I think the field is not new to most of you. So multiferroics actually are the ones actually in which there are two ferroic forms of ordering in the same phase. That is ferroelectricity, ferromagnetism, or ferroelasticity. Magnetoelectric multiferroics are indeed more important because the coupling is the one that makes the memory 4 times larger than the simple memory. And also you can suitably switch the polarization by magnetic field and magnetization by electric field. There are a lot of device potentials, and some of them are mentioned here. And this is you can do multitask, and also can lead to the device miniaturization. And all this actually that makes it very important to work on multiferroic materials. You can have multi-state memory devices that is write ferroelectrically and read magneto-optically. Electric field controlled ferromagnetic resonance devices and magnetic data storage. You can have magnetic field induced changes in electric polarization. That means you can use as magnetic sensor. In fact, as low as 10⁻⁻18, you can still measure with this kind of materials. Actuators, transducers, that is magnetic electric control gives an additional degree of freedom, so they can be utilized when actuators are transducers. Dual tunability for microwave is very important for most of the defense or communication these days, and this is also we are working in that area. Multiferroic based tunnel junctions, which is good for Spintronics applications. So, but what are the problems and challenges? Well, only a few single phase multiferroic materials exist in nature. There's weak coupling between the electric field and magnetic order parameters. And so our task was that we started about 8 years ago, designing room temperature multiferroic materials with a strong MA coupling. In order to do that, we had to actually, one of the probably largest contribution in this area to start this research on looking for the new materials was Dr. Ashok Kumar, who is actually at the NPL in India these days. So what we decided, we started working on that. Since PZT is lead zirconate titanate, is very well known material that makes actually solid solutions with many of the lead-based compounds. So we decided to have the actually make the PZT we chose 3 multiferroic materials. One is PFW, that is lead iron tungstate, lead iron niobate, and lead iron tantalate. We chose these materials because all of those materials are indeed multiferroic by themselves. Unfortunately, they are multiferroic, but not at room temperature. They are at lower temperature. As you can see, the PFW, for example, the TC is 180 K, TN is 380 K. That is, the magnetic transition is at above room temperature, but the ferroelectric transition is below room temperature. PFT, which is tantalate, you have got ferroelectric transition above room temperature, but the magnetic transition is below room temperature. And PFN, which is niobate, the ferroelectric transition is above room temperature and magnetic transition is below room temperature. In other words, actually, they are not a practical applications by themselves. So we combined these materials one by one, of course, made PFW with PGT, PFT with PGT, and PFN with PGT. We made separate solid solutions of this material. And in order to do that, we utilize ceramic sample preparation technique in our lab. We chose all kinds of oxide chemicals, lead oxide, zirconium oxide, titanium oxide, iron oxide, or tantalum oxide, or niobium oxide. I'm actually here reporting many of the examples that I'll give will be the lead iron niobate and lead iron tantalate with PGT. And in short form, we'll call it PGT-FT, that is the lead iron tantalate, and PGT FN, that is lead iron niobate. We have prepared all kinds of concentrations, as you can say. The X actually, that is the what should be the each content. It is quickly from 0.1 to 0.9. You can see all of them were made, both for PFN and PCT, and also PFT and PCT. And here are, of course, growth conditions are given and what temperature we have grown them. Okay, we carried out the XRD studies. Here we are showing only a few examples in order to have clarity, although we made for all of the concentrations. And we found actually the XRD patterns reveal single phase perovskite structures without secondary phases within the detection limit of the equipment. And for all concentrations that was found. So that was great actually, because you see, this is considered excellent results because the center of the perovskite octahedra are occupied randomly by zirconium, titanium, iron, and tantalate or niobate. We carried out actually the SEM studies, EDUX, and also the STM EDUX for each of these component materials that we prepared. And we found that their bi-elemental mapping is showing that we have really single gain clearly reveals the presence of all elements of the compound with homogeneous distribution throughout the grain. We carried out high temperature studies, X-ray studies on these materials. Here I'm giving two examples, that is X equal to 0.4 and also X equal to 0.3. And you can see here that at lower temperature, the XRD peak showed characteristic orthorhombic splitting. That is, means you have got 002, 200, and 020, or the other peak like 112, 211, 111, 121, which merge and become just the two peaks at higher. Maybe I can show. Yeah, you can see here. Actually, it becomes at higher temperature. It becomes actually only two peaks become actually later on. This has to be expanded, and this is what is done here. And this is expanded and shown here. You can see same thing in this side. You have three peaks, and they become two peaks actually at higher temperatures. So that shows actually that the materials are changing from orthorhombic to tetragonal phase. In fact, here you can see even more details. We have the how the A component, I mean the A lattice parameters changes. And here you have got the dielectric anomalies. see, you can clearly see that this is where the dielectric, all at various frequencies, you see the dielectric maximum is here somewhere. So that means that's where the tension is there. And that shows from XRD also. You have got two parameters here, that is A and C, and you have got ABC here. So this is orthorhombic phase. This is tetragonal phase. And you can see from the dielectric data as well. So here is dielectric loss. And one thing interesting, the losses were low. And this is, of course, for another composition, that is X equal to 0.3. And X equal to 0.3, we can say that this is the tension is around 520. And X equal to 0.4, the tension is 475. And then based on our symmetry transformation rules, we assigned PMM2, that is the orthorhombic phase, and P4MM as the space group for the tetragonal phase. We carried out more studies on that. Actually, we studied phonons by Raman spectroscopy at 3 different temperatures, that is 300K and 523 and 1123. And these spectra are very complicated, so we had to deconvolute. We found that we needed 12 peaks to fit this spectrum, 8 peaks to this one and this one. And that clearly shows that this is orthorhombic, this tetragonal, and in cubic, you should not see any peaks. So as a result, actually, you can see the cubic spectrum. So all these studies are agreeing with each other. We have carried out actually dielectric measurements for all the concentrations, all various X concentrations, and found that the peak position changes considerably. That means the transition temperature changes considerably. We find the transition temperature actually decreased from 687 to 453 degree for the PFN, and from 528 degree to 340 degree for the PGT PFT. We did ferroelectric measurements, that is the polarization measurements, and for various concentrations, you can see it is there. You will see most, probably one of the best values that can be assigned in this region. And the polarization, a remnant polarization was between 20 to 30 for the PFN PGT, or for the PFT PGT, it was 10 to 16. So we had more polarization for the PFN PGT. The magnetic measurements, you can clearly see for all concentrations, you see the magnetic measurements. Here they are depicted for both PFN PGT and PFT PGT. Probably the best values are for X equal to 0.2 and 0.3 because remnant magnetization is maximum. We tried to do the magnetic measurements, magnetization is at lower temperatures. We went right up to close to the, point, 4 degree K or something like that. And we find that around 30 K, it sharply increases that. But more interesting thing is that we did not see any anomaly around 180 K, where supposed PFT is supposed to have a magnetic transition. We don't see any anomaly. So that means the PFT by itself is not present, as this component is not present by itself in the composite material. And similarly, other other impurity phases that could have been seen were iron oxide and two different kinds. Each one has got magnetic transition is 260 K, and this one has got 120 K. We do not see any such peaks, so that means these impurity ions are not present. Here are the leakage currents for PGT PFN and PGT PFT ceramics. We find the leakage currents are really very low, and this is in fact this is very much required for the device purposes, low leakage current. So because high dielectric constant, low losses, and low leakage currents are extremely important parameters for the device. We decided to make some thin films. I give you only one example here. We chose PGT, we chose PGT PFT, in this case by pulse laser deposition, and we utilized magnesium oxide as substrate and LSCO as bottom electrode in order not to confuse with the magnetism coming from from the bottom electrode. So we chose LSCO and PGT PFT material that we deposited. These are the deposition parameters. Okay, you can see from the XRD spectrum that it is indeed very much oriented film. I could not call it actually epitaxial, but it is nearly epitaxial. You can see that actually the only 001 peaks are present, 002, and 0011, a peak is only 0.01% of the most intense peak in the targets. So that shows actually that the other orientations are very much, in peakest one. And surface reference by AFM was around 20 nanometers. Well, here you can see very interesting and nice ferroelectric loop and PGT PFT. And here I've shown for different AX values that 0.2, 0.3, you've got 0.1 and 0.4 are here. But this is very interesting, very good loop, considering there could be oxygen vacancies which really destroy the loop actually, and leakage currents and all that. But since leakage current is very low, we can get very excellent loop in this case. Here are the magnetic properties. You can see that also is an excellent loop. We have done these dielectric measurements on these films, and dielectric constant is quite high. As you can see here, there's some relaxation behavior. Actually, relaxer behavior is there because you can see with the frequency, the peak shifting, and this can be. So there is and the films are actually indeed relaxer in this case is less for 0.3 and more for 0.4. This material, these films we have done in Professor Srinivasan's lab, actually magnetoelectric coupling. And you can see it's a very strong magnetoelectric material actually. You can see 17.3 volts per centimeter. This is very high value actually. So we can conclude from this one that PGT FT with the concentration of 0.4 or 0.3 has got is very nice, suitable material for the magnetoelectric coupling. So in conclusion to this part, I would say we have successfully synthesized PGT PFN, PGT PFT, and PGT PFW multiferric. I did not give much details of multiferric because it would have been almost duplication as it happens in the other materials. This has also behaved very well actually when you're talking about the multiferric properties. The existence of multiferroism in all these systems opens the possibility to explore new family of multiferric materials at room temperature. And of course, there are lots of scientists all over the world are trying to make different materials and to look out for the multiferric properties. Multiferroy in thin films of this PGT, FT, and the LSMO had shown giant magnetoelectric coupling at room temperature. Okay, recently we started working on another material, which is also important because the density functional theory has shown that if you dope PGT or PT with palladium, then you could get magnetism in that. Now that is possible. You see, if PD4, that is the palladium, replaces the titanium, that is the octahedral center, then you get magnetism only of 0.1 Bohr magneton. Now, but if PD4 replaces lead ion, that is the corner atom, then you can get magnetic moment as high as 1 micro Bohr. So we decided to make this material and we chose PGT 2080, and also then we doped this with palladium 10% and 30%, and these are the. So here are the XRD studies actually of the pure tetragonal phase of material was seen, and tetragonality ratio was 1.07. there was a small peak due to the lead oxide. Is less than less than 1% actually, and this peak, this of course this material is magnetic, but magnetism of this one, since material is very small amount, it should not be affecting a lot our work. Three-dimensional schematic, see how the palladium is going into different sites. It's shown here. We did, in order to understand where is palladium going. Is it going in A site, or is it going to B site, or is it going in both sides? We did some the XPS studies, and you can see from here, from XPS spectra, that PD is in both the forms. That is the +2, which is going to the A site, and +4 going to the B site. It was found that it occurs in both the sites. It is existing, and the amount of A or B sites is actually, the ratio is 4/3. That is 3 in B site, then 4 will be in, 4 will be in B site and 3 will be in A site. And here is actually the binding of the oxygen in that case. We did dielectric measurements, and we find systematically this material has a transition temperature here, somewhere at this point, which is 569 degree K. And this is from the DSC measurements actually, that we find a peak, which is around 552. We did what's called the magnetoelectric measurements in this material. The magnetoelectric coefficients, you can see it's now in millivolts. It's not very high, but there is indeed a coupling is there, but it's not too high as we saw in the PGTFT thin films. But it is significant, and it can be utilized for the magnetopheric properties. Here actually, that was in PT, and this is in PGT-PD. The magnetoelectric coupling is, the values are more or less the same. That it does have a coupling, but they have the order of 0.3. So the data that I have shown you so far is on ceramic materials, whether PGT-PD or PT-PD. So we decided to make some thin films of this material as well. So it's a normal process. Actually, we have bottom electrode, LSMO, and we grew an LSAT, and we prepared this material that is 30% and also 10%, and we carried out this work. So the thin films actually, they stabilize in perovskite tetragonal phase with 100 oriented, basically 100, highly oriented 200, 100, all of that. So no impurity peaks indicating phase pure films. The compressive lattice strain on the film was around 2% in this case. Okay, here you have got the FM that shows actually the RMS roughness of around 0.4 nanometer. And here you have got actually the ED spectrum. You can see there is uniform distribution of all elements, actually lead, titanium, oxygen, and other ones. We did PFM studies in this material, and you can see that there is a amplitude change and phase changes images of this material as you go, for different voltages. So polar switching behavior suggesting the ferroelectricity at nanoscale. This material has a lot of oxygen vacancies. As a result, actually, it's very leaky, actually. As a result, you cannot get a good ferroelectric loop in this material. And the dielectric properties, we cannot go beyond this limit, actually. So we don't know what is happening there, actually, whether this is due to the high temperature leakage of dielectric constant that occurs normally. We do see there's a slight change with the frequency that we see in this material. So it's rather difficult to come to a conclusion to whether the leakage is due to the oxygens or some other behavior is taking place in this. We have magnetic properties. Yes, this material did show the magnetic properties, as you can see. And here is the variation of remnant magnetization. Here's the XPS data on this material, which is exactly similar to what we have been talking in the in the ceramic materials. So we see in the thin film also, you've got PD4 and PD2 in this material. Here is another thing that we have shown so far is the PTPD thin films. Now we made PGTPD thin films as well. And the same techniques, and these are the growth conditions of this material. And here also you can see that the material actually are grown. Thin films are grown in the 001 orientation, so they are highly, let's say, not epitaxial, but I would say actually it's highly oriented materials. And thickness of the film here we're measuring is about 300 nanometers. RMS value is very similar to what we had reported earlier. It's around 5.4 and very uniform. You can see crack-free and surface and roughness of the material. Here is actually you can see the EDX studies actually, and the EDS has got very homogeneous distribution of all elements. It can be seen in there. The dielectric constant here as a function of temperature, we can see some peak, coming up here, and this peak could be the phase transition, which is around 515K in this material. The ferroelectric loop is very leaky, and that's due to the oxygen vacancies, because remember when PD goes into the A site, it will have a 2 valency, and as a result, it creates enormous oxygen vacancies in that. And and this that causes a lot of conduction. As a result, the ferroelectric loop is difficult to have a nice loop in this material. Here are magnetic properties. The magnetic loop is actually, you can see, it does show that this material can be made magnetic by adding palladium at the A site. And that purpose is that you can clearly see in this case. So in conclusion to this one, we'll say PD substituted materials, lead titanate or lead zirconiate titanate, do show the multiferroic properties, and as suggested by the theory, and the evidence of mixed oxidation states of lead, the palladium ion, that is PD4 and PD2 from XPS existed that fulfill magnetic ordering conditions. Dielectric studies suggest a ferroelectric paraelectric phase transition around 515K. Me coupling existed in all of these materials at room temperature, though small. Well, I'm now concluded my presentation, and this work was supported by the Department of Energy, National Science Foundation, and Department of Defense. And you may look at this website for relevant publications, and also the Spec Lab facilities. So I conclude my talk, and I'm ready for any questions or anything like that. Well, these are the facilities that are existing at the University of Puerto Rico in the Spec Lab.
So thank you very much, Professor Katiyar, for timely finishing the talk. And now, if anybody has any questions, please they can post it, or they can wave their hand. Okay, there is one question, sir. The question is,
Yes.
Can band gap tuning in MGO results in multiferroic properties?
In MGO?
Yeah, somebody has asked.
It is the MGO. MGO is, that it has got very wide band gap actually.
Yeah.
So it's not the band gap tuning will go. It is the how you make the MGO ferroelectric and ferromagnetic. Both properties are not there in MGO. It's neither ferroelectric nor ferromagnetic. So you have to dope it with certain elements which can give magnetic properties. And also, you have to have ferroelectric properties, which is not just by simple doping, because that depends on the dipoles actually that you have to create, which are, remember, MgO is centrosymmetric. So you have to break its centrosymmetry, and it has to be one of the 10 space groups in that case actually, in which there is no center of inversion. So I think MgO will have, you have to do a lot of work to make MgO as a ferroelectric or multiferroelectric.
So there is another question, sir. Why the ferroelectric hysteresis loop in case of a bulk sample is not continuous, means there a gap is negative polarization axis, but in case of thin film it is absence.
Actually, the ceramic samples have got more oxygen vacancies and inhomogeneity. That actually is always problematic actually. Now, thin film, it is possible to have more uniform materials and better order actually. So I believe that could be the one. Impurities are something that may be responsible. Oxygen vacancies is one of the biggest problem actually in such materials.
Yeah. Yeah, so I think Professor Katiyar answered the question. So actually, sir, I have one question just to know. This BFO is well in your lab also. So say room temperature multi. So of course that is also single phase. So how that one will be comparable to the multiferroic?
Okay, BFO is a naturally occurring room temperature multiferroic. Everybody knows that actually that was one of the first materials because you don't have to do anything. BFO itself is a multiferroic at room temperature. I mean, there is antiferromagnetism. Actually, this is because it's canted in thin film. In thin films are actually multiferroic very simply because the magnetization is canted, so it gives you magnetization in that case. Ferromagnetic properties it gives. The biggest problem in BFO is it's very leaky actually. When it's very, very difficult. Some people have reported cleverly a very nice ferroelectric loop. What they did actually, they used a high frequency, radiant technology bridge, which is not right actually, because you should have at low frequency, you should have a good ferroelectric loop. So you otherwise you get like a loop in banana, some kind of circular, and that is the biggest one of the problems. Second problem is a coupling is not very strong actually in that. We are looking for materials in which we can use internal junctions and things like that, where you have got something like, 6 to 7 nanometer of thickness and all that. And you want actually to switch. And if you make BFO has not been possible to make, which is not leaky, very much. So leakage current is one of the biggest problem, I would say.
Another question, what was the reason behind dielectric dispersion over the whole temperature range? So actually it is not my question. These are the questions posted by the audience. So I am
Yes,
asking question on behalf of the audience. So this is the question is, what was the reason behind the dielectric dispersion over the whole temperature range?
The reason is that at a higher temperature, you have a lot of oxygen conductivity comes into picture, and you cannot measure the dielectric constant by the ordinary bridge, actually above many places, about 600 degree or something like that above that, because of the, conductivity increases considerably in these materials.
So there is one more question, sir. PZT, PD, which type of multiferroic material?
Well, this is a multiferroic material in the sense that PD is going into the A site, and A site means 2+. So because it is a transition element, it can change the valency. That's not so that way, but it does cause lots of oxygen vacancies as well. So as a result, the material remains leaky. One has to work out a better way of actually, making this material. So it is doped. I would consider it is a PZT doped. I mean PD doped PZT material.
Okay. So if there is no more questions, let's thank Prof. Katiyar for his a nice presentation, and I hope that his presentation has made impact on the audience, and particularly the young students who were attending this talk. And I encourage they can go to his website and see his full publication kind of work that Professor Katiyar is carrying out. Thank you very much. Now over for us, sir.
Many thanks, sir. Professor Katiyar, a very nice presentation. And yesterday night, when I saw your mail, I think we have no problem, and Satya Prakash did the job well, so no problem in the share screening. Thank you for a wonderful talk, and your talk will going to excite the complete young generation of all over the world, and you giving a new path for the new materials, next generation ferrite material and piezoelectric materials, and hope some high temperature material very soon come in your laboratory, so that a new thought, new device fabrications that are going to industrial applications, which is need of the whole world, that people are struggling. And I'm very confident the way definitely the today's talk going to have a complete breakthrough, I can say, for the young generation, sir. So thank you very much accepting the invitation on behalf of our KIIT University, on behalf of organizing committee. I have a special gratitude and thank you. And after the lockdown period, definitely I'll call you in the KIIT University and have some a strong bonding collaboration in the next generation materials. So thank you.
In this connection, I may add a bit, actually, a few words that
Yes,
we have got a single lab which has got almost all kinds of facilities, taking from magnetism to ferroelectric and battery materials and photovoltaic materials. We have excellent facilities created actually over the 30 years or so. Now, I just want to tell you that anybody from India, from any university, researcher, student, faculty member is welcome to utilize the facilities. You know that most of the places in the United States are there is a big charge for utilizing the facilities. However, we do not charge anything actually, as long as I am there. These facilities are at no cost, and we can even help you in some materials, purchases and various kinds of things actually that you require actually, and these are available at no cost. But you have to have your own expenses to live and also travel. I believe Government of India may have some scholarships, and I know many of the Indians are coming, for short term, like 6 months or a year, and they have been utilizing the facilities actually. Okay.
So thank you very much, sir. And this is a big contribution in what you are doing. So that is great. There's no word how I can give you thank you, sir. This is great. Really, your support, the chemical support, all kind of support you are doing, we know, and you have made many young scientists from your laboratory. I can say the maximum people all over the world who are working in the ferrite, others, they are anyhow connected with you. Not a single person I can say they are not connected with you. So I can say as you made a big tree of ferrite or multiferrite, and you are Godfather, sir. Thank you very much. And thank you again on behalf of our KIIT University, and as a organizing committee on School of Applied Sciences, sir. Thank you very much. Namaskar, sir.
Thank you. Okay. All right.
Namaskar.
I will leave.
Okay, sir. Thank you very much, sir.
Okay. Okay. Satya.
Thank you very much, Satyaprakash, sir, and
you on
chairing this session. And it is a coincidence that you are from also the same laboratory. So meeting with the same guardian, I can say. So it is a wonderful meeting
Yes.
with your.
Thank you. Thank you very much for making the.
Thank you very
much for making the connection.
Okay. All right.
Yeah. Okay.
So tomorrow we have we are going to meet at 9:30 sharp. The talk will start 9:30. So thank you very much to joining tomorrow, and I hope all of you have enjoyed today. So tomorrow, very good talk, industry talk also there, and variety of talk of advances and functional materials are there. And tomorrow also the declaration of the Young Scientist Award. So many of the people are waiting who are going to have the new Young Scientist Award in the advanced functional material. So valedictory time will declare those things. So thank you very much to join tomorrow. So 9:30, and today we are going to end this session. Thank you very much. Thank you, sir, Satyaprakash, sir. Thank you everyone for joining today. Thank you very much.